Hello everyone, welcome to the instructions or the help for the electrostatics and E-fields practice problems that I gave out in class. There were 6 problems. I think I'll be able to fit this in one video, but I might split up into 2. I guess we'll find out later. So let's get started, and let me apologize in advance for any coughing or sneezing. I do have a bit of a cold, so I hope that that doesn't come through in the video. So here we go. A charged object with a charge of -6 nanocoulombs remains at rest at position x, which is equal to 1.0 meters, so at x equals 1 meters. Find the magnitude and direction of the E field at x equals 0.6 meters, positive 0.6 meters. At what location or locations does the E field have a magnitude of 4 newtons per coulomb for part B? So what I've done here is I've drawn effectively a number line, since this is what this is talking about. It's all has to do with like the x-axis. So what we can do is we'll set a point here as the origin, and I will try and do some fairly even tick marks, 2, 4, 6, 8, and then 1. So this is the 1 meter mark, positive 1 meter mark. And there is a charge here that is -6 nanocoulombs. Now, nanocoulombs is not just -6. Nanocoulombs means -6 times 10 to the -9 coulombs. So for later, when we're doing all this math, we'll need to make sure that we keep that in mind. Now, the question asks, find the magnitude and direction of the E field at x is equal to positive 0.6 meters. So this is 0.2, 0.4, here's 0.6 meters. And so we're looking for the E field at this point. So this is a point charge, and we know already that from the equations that we've used that the E field on a point charge, or from a point charge, is equal to K, which is Coulomb's constant, times the source charge, the absolute value for now, over the distance away squared. So in this case, our K, well, K is always 9 times 10 to the 9th, newtons meters squared over coulomb squared. I'm just going to write that once just this time so you remember what the units are, but in the future I'm going to leave that out because it takes forever to write. Q source is our source charge, which is the -6 times 10 to the -9 coulombs. And our distance is not, excuse me, is not the 1 meter. Here it is the distance from the source charge to wherever it is we are measuring our E field, 0.2. So that would be here. If you can hear that helicopter or plane, my apologies. So this, this is not 0.6 meters, this is 0.4 meters from 1 meter to 0.6 meters. So we're going to have 0.4 meters here, and don't forget to square it. That is something that people forget all the time. And when you go through this math, you end up with an E field strength of about 337.5 newtons per coulomb. So that was part A. That was not bad. The next part asks, at what location or locations does the E field have a magnitude of 4 newtons per coulomb? Oh, which reminds me. So we know the magnitude of the E field at this point, but we never said the direction. Since this is a negative charge, right, for negative charges, the E field lines all point inward towards it, right? Because a positive test charge would feel an attractive force pulling it in towards the negative charge. So at this point, if all the E field lines for a negative charge are pointing inward, that means that this E field is going to be this magnitude in the positive x direction in this case. Positive x direction. So for part B, at what location or locations does the E field have a magnitude of 4 newtons per coulomb? So in this case, instead of being given all this and asked to find the E field strength, we are given the E field strength and asked to find the distance away. So what we can do is we can using this equation, we could solve for R, which is a simple cross multiplication sort of thing. So you've got E R squared is equal to K Q source over nothing, because we already did over R squared. And solving for R, we get the square root of KQ source over E. And then when you plug this in, I'm not going to write it out, but when you plug in all these numbers, you get a distance of 3.67 meters. Pretty far. Now, this is the distance. You'll notice that because we are on a number line here, right, that is 3.67 meters away from this point, from, the 1 meter mark. So, at what locations implies the actual points on the number line that you would find this E field strength. So that is either 3.67 meters away in this direction, the positive direction from 1 meter, or in the negative direction from 1 meter. So you would find this at the points x is equal to positive 4.67 meters, or at the negative 2.67 meters. All right. So at either of these points, you will find an E field strength of 4 newtons per coulomb. All right, let's move on down. A charge Q1 equals 5 microcoulombs, is at the origin, and a second charge, negative 3 microcoulombs, is on the x-axis at plus 0.8 meters from the origin. Find the E field strength at a point 0.4 meters from the origin. Find the E field strength at point on the x-axis negative 0.4 meters from the origin. So what we're going to do is we're going to draw a similar number line that I did before. We'll define our origin somewhere in the middle here, and just drew some tick marks. There's 10 tick marks here, so this would be at the 1 meter mark, which means that this here is 0.8 meters, and this here is 0.1, 0.2, 0.3, 0.4 meters. And so we have one charge here at the origin, which is a positive charge and has a charge of 5 microcoulombs, that is to say 5 times 10 to the negative 6 coulombs. Then we have another charge at 0.8 meters, which is over here. This one, Q2, this is Q1, this is Q2, has a negative charge of 3 microcoulombs times 10 to the negative 6 coulombs. All right, and so we are asked to find the E field at a point 0.4 over here, and at a point negative 0.4, 2, 3, 4 over here. Since we have 2 point charges now, we can't just do one solution, because each of these point charges is going to create a separate E field at this point. Once we find the E field from each of these at this point, sort of like the quiz we took, we can then add those E fields together in some way to find the net E field. So let's start with part A. So at that point, I'm just going to redraw it here, the negative charge has an E field that points towards it, always, right? A positive test charge here would feel a pull towards this, and this positive charge, Q1, is going to be pushing away here as well. So we've got one E field from Q1 pointing in the positive x direction. We've got another E field from Q2 pointing in the positive x direction. So what you're going to have is E1 and E2, which is slightly smaller. We'll talk about why in a sec. Both pointing in the positive x direction. So when we find each of these magnitudes, in this case we can actually just add them together because they're both pointing in the same direction on the same axis. To do that, we would simply use that same equation we used before. E is equal to k q source over r squared. So for E1, this is k, which is 9 times 10 to the 9th, times Q1, which is 5 times 10 to the negative 6 coulombs. Notice I put the absolute value over the distance, which in this case is 0.4 meters squared. This, when you plug it in, comes out to 2812 0.50 newtons per coulomb. Then for E2, you would go through a similar process, plug in the values for E2. So in this case, this is going to be K, which is 9 times 10 to the 9th, times 3 times 10 to the negative 6 coulombs over the distance, which is also 0.4 meters, right? 1, 2, 3, 4. 0.4 meters, don't forget to square it. This comes out to 168,750 newtons per coulomb. So since we are just adding these together, we can simply add these two numbers to get E net, or the net E field, which is equal to the very nice 450,000 newtons per coulomb. So that is the net E field at a point 0.4 meters, a positive 0.4 meters on the x-axis. And this is obviously pointing in the positive x direction. Now, for this point here in part B, it's slightly different. We have the E field from Q1 at this point now not pointing to the right because it's Q1 has E fields going away from it, right? So a positive charge here would feel a force pushing away from Q1. So E1 is actually going to be in this direction, while E2 from the negative charge is still going to be pulling towards it, now much less so because it's so far away. So this is going to be E2. So this time when we set it up, we'll make sure that this is still the positive x direction. When we set it up, now E2 is going to be positive, but because E1 is pointing in the negative x direction, we'll make E1 negative. So when we do this, we do the same process here. We plug it into this equation. You'll notice that for E1, everything is almost exactly the same, except that it's pointing in the negative direction. So the magnitude is still the same because it's the same distance away and it's the same charge, right? It's 0.4 meters from the origin. But because it's in the negative direction, we'll just make this a negative this number, 281,250 newtons per coulomb. Plugging everything in for this one now with our new distance, which is actually going to be the entire distance from here to here, which is 1.2. E2 is going to be K times 3 times 10 to the negative 6 coulombs over the distance 1.2 meters squared. This comes out to 18,750 newtons per coulomb. Now we said we are going to add these two together. Now this is negative and this is positive, so when you add these, you end up with an E net, I'm going to do this over here, is going to be equal to negative 262,500 newtons per coulomb, pointing in the negative x direction, or negative x. All right, so that is the solution to part B. Moving right along. All right, problem 3. In some region of space, there's a uniform electric field of magnitude 3 times 10 to the 5th newtons per coulomb that points to the right, created by a charged metal plate. Mike places a 500-gram cart, important to remember that, in the region. On top of the cart, there's a metal conducting sphere with a charge of negative 2 nanocoulombs. Excuse me. Draw a force diagram for the cart. What is the test charge? What is the source of the E field? Determine the force exerted on the cart and the resultant acceleration. How did you do this? So the first thing we have to do is draw our sketch. So we have a uniform E field, uniform electric field, pointing to the right. So that's going to look something like that. I will try and draw it as uniform as possible. Uniform obviously means that regardless of the distance away, the E field strength does not change. And this has a magnitude of 3 times 10 to the 5th newtons per coulomb. And then in this, and this is being created, of course, by a plate, by a charged plate. Now, if this is a uniform field pointing to the right, this plate would then obviously have to be positive because the E field lines always point away from the positive charge and towards a negative charge. So this would have to be a positive plate here. In here, there is this cart, this magical cart with a charge on it. This charge is a negative charge and has a charge of 2 times 10 to the negative 9th coulombs. That is 2 nanocoulombs. All right, and so draw a force diagram for the cart. So if our cart is the system, then our force diagram, A, is simply going to be the upward normal force, otherwise known as the force of the ground on the cart. We've got our downward force, which is equal to the upward force, despite what that arrow looks like, of the earth on the cart. And to the left here, we have the force of the E field on cart. Now, why is it to the left? Because these E field lines represent the force that would be exerted on a positive test charge, right? So if this was a positive charge in here, it would experience a force being pushed away from this positive plate. But because this is a negative charge on this cart, the cart is experiencing a force to the left in the opposite direction of the E field. So an important thing to remember is that E field lines only point in the direction that a positive charge would feel a force, right? So if it is a negative charge experiences a force opposite in the direction of the E field lines. Very important to remember. So that is why this force is to the left. We'll notice that there's only going to be an acceleration in the x direction because that is the only direction in which there is an unbalanced force. So when we go to part B, this is actually just a conceptual question. What is the test charge and what is the source of the E field? The test charge in this case is our charge on the cart, because that is the charge that we are placing into this E field. The source of the E field is this charged plate. We don't know what the charge on this plate is. We don't actually need to know because we're given the strength of the E field already, which doesn't change regardless of how far you get. So I guess forgetting about part B now, since we just talked about it, and doing part C, the force exerted on the cart and the resultant acceleration. So to find the force of the E field on the cart, right, which is the only one that is causing acceleration, there's an equation for this. The force of E field on any charge is going to be Q, the charge, or the test charge, times the E field strength. In this case, Q we said was 2 times 10 to the negative 9th coulombs, 2 nanocoulombs. And the E field strength is 3 times 10 to the 5th newtons per coulomb. So when you do this math out, you get 6 times 10 to the negative 4th newtons. All right, you'll notice the coulombs here and the coulombs here will cancel out, resulting in a unit of newtons up here, which is why you get this. So this is the force being exerted on this cart from the E field. Now, the acceleration in this case, since we know what the mass of the cart is and we know what the net force on the cart is, we can use our good friend Newton's second law, which is A is equal to the sum of the forces over the mass. You'll notice I put these x's here. That's because the acceleration and the net force is only in the x direction. Our acceleration is going to be our net force, which is 6 times 10 to the negative 4 newtons. Technically, if this is the positive direction, this would be in the negative direction, so this would be a negative force, over our mass, which is 500 grams. If it is 500 grams, this has to be in kilograms, so this is going to be 0.5 kilograms. This will give us an acceleration of 1.2 times 10 to the negative 3 meters per second squared. Not a huge acceleration. And to do this, like I just said, we find the net force on the cart in the x direction. We use the force diagram to draw to solve for our force, right? And then we use Newton's second law to simply solve for the E field strength, to solve for the acceleration using Newton's second law. Pretty simple. Moving right along. Alright, so we have here a ball hanging from a string. The ball has a mass of 0.6 kilograms and is electrically charged. The string from which it is hanging is exerting a 1.4 Newton force upward on the ball. Apparently I cut out half this problem, no worries. Below the charged ball is a charged plate, which produces an E field. So here's our charged plate, and it's producing an E field that is pointing downward like this, which means the charge on this plate is actually negative, right? Because the E field is pointing down towards it. Complete the table that follows to determine the charge on the ball, sign, and magnitude. Assume that the gravitational constant G is 10 newtons per kilogram. So this is going to be little g is going to be 10. So, and the first thing we have to do, well, this is draw a force diagram for the hanging ball. We are making an assumption that the force of the plate on the ball is in this direction. We don't know that necessarily, because we don't know that if these two together add up to 1.4. We'll figure that out soon enough. Represent the diagram mathematically using Newton's second law. So the acceleration, Newton's second law, is A is equal to the sum of forces over the mass. We only have forces in the y direction, so we're only going to consider the forces in the y direction and the acceleration in the y direction. AY, in this case, is equal to the force, I'm going to have up be positive. So we have the force of the string on ball minus the force of the earth on the ball and the force of the plate on the object. Minus force plate on the ball. Alright, now this is all, obviously all divided by m. Sorry for having to go on the line below. That's okay though. So this is setting up Newton's second law. Now we have to solve for the charge on the ball. I'm going to do this over here. So one thing I want to point out, so because this is balanced, I'm assuming it's not accelerating, I don't think it is, these forces have to be balanced, right? Which means that these have to all add up to 0 acceleration. So we get 0 is equal to force string on ball minus force earth on ball minus this E field, the force of the plate, which is actually the E field, right? So force E field on ball. And this is all equal to 0 divided by m, but if you multiply m by both sides, you just get this. Now, here's a thing I want to point out. You'll notice that the force of the string on the ball we already know is 1.4 newtons. The force of the earth on the ball is just going to be mg, right, where the m is 0.6 kilograms, and g is our 10 newtons per kilogram, minus the force of the E field on the ball. Now, this, once you do the math, we got 1.4 newtons minus 6 newtons minus 4 E field, force E field on ball is equal to 0. Now, I don't know if you noticed this, but this here is going to be negative 4.6 newtons minus force E field on ball. Now this minus this has to equal 0. For this to be able to be 0, force E field actually has to be positive, which means that this force diagram is wrong, right? Do you see that? So for this to actually add up to this would have to be, we'd have to put a negative number in here, meaning that it's opposite the direction that this is pointing. So this force diagram is actually wrong. The correct force diagram would have to be this, which is the force of the string, and this, which is the force of the plate, all minus the force of the earth on the ball. This is the only way for this to be 1.4 newtons, for the force of the string to be 1.4 newtons, because the force that the earth exerts on the ball is already 6 newtons. So if the force of the earth on the ball is 6 newtons, then the force of the string on the ball would have to be more than 1.4 if the force of the plate was downward. See that? So this would have to be greater than 6 newtons, which is not. It's 1.4. So obviously the force of the plate is pushing up on the ball to balance out the force of the Earth, this 6 Newton force on the Earth, from the Earth on the ball. So the force of the E field on the ball would have to be this 4.6 newtons, right? When you solve this out, you add this to this side, it's going to be 4.6 newtons in the positive direction, right? 4.6 newtons up. That means that if this is the direction of our E field here, then the force that the E field is exerting is not down, which means that this can't be positive. If it were positive, it would feel a downward force, which it is not, which means that this has to be a negative charge. So we've done the first part and found the sign, right, of the charge on the ball, which is negative. Now it's just a matter of finding the actual charge of the ball. We know that the E field strength is 2 times 10 to the 5th newtons per coulomb. We know that force E field on, well, any object on Q is equal to Q times the E field strength. We know the E field strength, so we can solve for Q, which is just force E field on Q over this E field strength. In this case, this is 4.6 newtons over 2 times 10 to the 5th newtons per coulomb. This gives us a result of negative, technically, 2.3 times 10 to the negative 5th coulombs. I put the negative in there because it is a negative charge, right? Alright, let us move on. A 0.06 kilogram electrically charged ball hangs at the end of a string oriented 53 degrees downward, 53 degrees outward from a charged vertical plate. The E field produced by the plate at the position of the ball is 1 times 10 to the 5th newtons per coulomb, shown here, and points away from the plate, which means that this plate would have to be positive, just FYI. Complete the table and follows in to determine the charge on the ball, sign and magnitude. Assume that the gravitational constant is 10 newtons per kilogram. So immediately we can tell that since this ball is being pushed away from the plate, this ball would have to have a positive charge in order to do this because it's being repelled by this plate. So for the force diagram for this ball, we would have the force of the string, otherwise known as force tension, or hereby known as force tension, the force of the Earth on the ball, and the force of the E field on ball. Force E field on ball. Now, because everything here is stationary, we know that all these forces have to be balanced. We can redraw this and show that what this is actually doing is, if we break this up into components, right, we've got two components here. We've got the X component and the Y component. So here we've got force tension Y, and here we've got force Earth on ball. And here we have the E field strength, the E field, force the E field on the ball. And here we've got the X component, force tension in the X direction. So these are what we're going to use when we start representing our diagram mathematically using Newton's second law. So the acceleration in the X direction is equal to the sum of the forces in the X direction over the mass. Our forces in the X direction are, if I have the positive direction being this way and the positive Y direction being up, then we have force E field on ball minus force tension in the X direction all over the mass, and then the acceleration in the Y direction is equal to the sum of the forces in the Y direction for the mass, which is going to be force tension Y minus, well, force of Earth. Sorry about that, minus force Earth on ball over the mass. Sorry for the messy writing. Now, because all of this is balanced, both of these accelerations is 0, right? Which means that if AX is 0 and AY is 0, what effectively this comes down to is that the force force E field for the X direction on the ball is equal to force tension in the X direction. And in this case, force tension in the Y direction is equal to force Earth on ball. Now, to solve for the charge of the ball. So, the things we know. We know what the E field strength is. We don't know what the charge is. We don't know what the tension force is yet. All we really know is the mass and g, which means that we know what the force of Earth is. Now, so what's going to happen is, because we know what the force of Earth on the ball is, we can then use that and some trigonometry to find out what the force tension is. When we find out what the force tension is, we can use that in here to find out what the force of the E field is, and therefore what the charge of the ball is. So, let's start with this. We know that, well, let's set up this triangle, right? So this tension force we know is this way, right? But then we've got these two forces here. So this is going to be force tension X, this will be force tension Y, and this is our angle theta, and this is force tension, right? This angle is force tension, or this angled vector. So, using SOHCAHTOA, pick your favorite, we can write an expression for the x component as ft times, in this case, sine theta, and the y component is equal to ft times cosine theta. So, rewriting these expressions we have up here, namely this one and this one, we have force Earth on the ball, which is mg, is equal to, oh sorry, that's E field. Force of the E field on the ball, which is QE, is equal to the force of tension in the x direction, which is force tension sine theta. And then from this one, we have the force tension in the y direction, which is force tension cosine theta, is equal to the force of Earth on the ball, or is it this we go, which is mg. So what I'm going to do, you don't have to do this, you could solve for force tension because you know m and g, and then plug that number into here, and then solve for q. What I'm going to do is I'm going to algebraically solve this because things end up working pretty nicely. Force tension is equal to mg over cosine theta. If you plug this back into here, what you get is mg sine theta over cosine theta. We know this to be tan theta, right? So I'm going to rewrite this down here. So now what we have is QE is equal to mg tan theta, and then solving for Q, we've got mg tan theta all over E, where the mass is 0.06 kilograms, g is going to be 10, theta in this case is 53 degrees, make sure your calculator's in degrees, and the E field strength is 1 times 10 to the 5th newtons per coulomb. Plugging all of that in, you get a charge of 8 times 10 to the negative 6 coulombs. Ta-da. Alright, last one. You have a dust particle that has a mass that is very, very small, drifting to the right, not up or down, which means that it has no velocity in the x or y direction. That's going to become important later. And it has a charge of 1 times 10 to the negative 7th coulombs. And it encounters a uniform E field, as pictured, pointing downward. Determine the vertical speed after it moves a vertical distance of 1 meter. So, essentially, what we want to know is what is the motion of this object in the y direction. So, because we have this downward force, because it is positive, we have this downward force from the E field, we also have, so this is force E field on our charge, our dust particle. We also have a very small downward force from the Earth on the dust particle, which means that this is going to have an acceleration downward. Since this has an acceleration downward, our motion for the object in the y direction is going to be something like this, right? See how this is all coming together with a delta v pointing down, which means that to find out its final velocity at a given position, we have to use a kinematics equation. seeing as how we're only given, well, we know that v initial is equal to 0 because it says it's not moving up or down, v initial y. We know that we have to find its acceleration using some force diagrams, some clever force diagrams, and we are looking for delta x, determine its vertical, sorry, we're looking for its final velocity after it has moved a distance of 1 meter. So after delta x is 1 meter. Since there is no time here, this all points to the timeless equation. V final squared is equal to V initial squared plus 2a delta x, or delta y in this case. So when we find our acceleration later, we'll be able to plug it into this to find our final velocity. But first we have to find the acceleration. So our acceleration can be found using Newton's second law. The acceleration in the y direction, I'm going to make, for the sake of it, I'm going to make downward be positive y, just so that everything turns out easy later. So we have our force Earth on the dust particle. So this is the sum of the forces in the y direction. Force Earth on the dust particle plus force E field on the dust particle all over the mass of the dust particle. That means, so the force of the Earth on the dust particle is the mass times g, which we will say is 10, plus the force of the E field, which is q times the E field strength. The q is the charge of the particle, E is the E field strength, all over the mass of the dust particle. Plugging this all in, the various numbers that are given in the problem, here's your E, here's your charge. Be careful when you plug in the mass. Since it is 0.001 grams, it is actually 0.000001 kilograms, or 1 times 10 to the negative 1, 2, 3, 4, 5, 6, negative 6 kilograms. So that is what you need to use for your mass. Be careful there. Once you plug everything in, you will get yourself an acceleration of 10 meters per second squared. Now that you have the acceleration, you can plug that into here. V final is going to be the square root. Our V initial is 0, so we can ignore it, of 2 times the acceleration, which is 10 meters per second squared, times our displacement, which is 1 meter. Plugging this all in, you get a final velocity of roughly 45 meters per second. Wow. All right, there you have it. Hope that was helpful, and good luck studying. Hopefully I will put up a few more of these videos while we are getting ready for the finals, maybe with some explanations of some more complicated problems. Good luck, and see you next time.